Now we're going to show you some important concept by using orange. Okay. The first thing I would like to show you is the regularization. Let's take a look at the one of the database, which is housing. Okay, and housing, those in housing data set, all features are numeric data, and its target is also numeric. Okay, so we can take a look at the data set by using data table, and you can see that all those features are numeric data, and Y target is also numeric. Okay, so we can do a test, okay, by using the data right here, and since it is a regression problem, so we can use, for example, linear regression. Okay, so there's important things of linear regression is that you can simply just open the configuration dialog, and you can see that there is a fit intercept, which means in our model we should model the intercept. Okay, so make sure it is checked. And for the regularization, and no regularization means the model is simply just y equals ax plus b, and we use MSE to perform the gradient descent, and you can see that the MSE value is 23, right? And make sure you understand that when we talk about training testing, okay, the test widget right here, okay, the default setting is cross validation. Cross validation is not validation dataset. That means you divide the entire training dataset into 10 different sub datasets, and you run the test 10 times, and for each test, okay, one sub dataset is used for testing, and the other 9 dataset in the training data are used as training dataset. Okay, so you have 10 different sub dataset to be used as testing dataset, and the corresponding 9 other dataset are used as training dataset. Okay, so the MSE right here, actually it is the average of 10 different testing dataset. Okay, so that is, and if you don't want to do so, okay, maybe another way to do testing is something like that. First, you get a data sample right here, and you can see that we can divide the original dataset into 2 different sub datasets, and here's the proportion. So you can use 2 different data table, okay, right here, and you can see that the upper one, okay, the upper one is the data sample. Okay, so that is the 80% of the data, because we said 80% right here. And below one, okay, you can use the remaining data as the second data set. And for the testing, okay, you can choose test on test data, and that means you use the upper data set as the training data, okay, and you use the rest of the 20% of the data as the testing data, so that you can perform testing by using the training data and testing data. And because we separate the data, right, by using the sampler, so basically while training the model, the linear regression model, only use the 80% of data for training and 20% for testing, and those testing data would never be used for training. Okay, it is only used for testing. So I think that is another way to test your model. Okay, so that is the first one. And the second thing that I would like to talk about is regression. So again, here we have a linear regression model, but right here I would like to check L2. Okay, so that is a linear regression L2. Okay, and the other one I like to use, okay, I put it right here. This one is linear regression and L1. Okay, so that is since we have L2, L1, and vanilla linear regression, they have different optimization function. Okay, so basically as you know, okay, if you sort MSE value, okay, and you can see that the original version of linear regression has lowest MSE. That is because it is optimized, right? But when you use L2 or L1, they add the regression item, okay, behind the MSE, so the MS value will be a little bit higher. Okay, that is how it works, right? And we can add a data table right here, and so it can output a coefficient, okay, to a data table. But make sure you still input the data to this model so that the coefficient can be calculated. Okay, so you can see that we can have the coefficient of different features right here, and we talk about the value of the coefficient. Okay, if the absolute value of a coefficient is larger, okay, for example NOx right here, CHAS right here, and maybe DIS right here. Okay, those coefficient, the absolute value of those coefficient are larger, right? So that means they are sensitive to the model. So, and also you can simply just use the rank right here, right? The rank right here, and we can calculate several different values, okay, right here, and it also indicate which features are more important than the others. Okay, so that is one of course, there are some other algorithms, they can help us to figure out which features are more important than the others. Okay, but basically it should be very close to the result right here. And as we mentioned, there are 14 different parameters in this linear regression, right? Because we have 13 features and one intercept. And if you apply, okay, again, okay, if you apply regression, especially lasso right here, and we can see that this value, okay, since we have the we minimize the sum of the coefficient, okay, in our cost function, so part of the coefficient right here should be close to 0. Okay, and as we mentioned, there is a weight. Okay, there's a weight in your cost function. In our class note, okay, we use lambda, right? But right here the weight is alpha, so you can simply just adjust this alpha value. If this alpha value is very close to 0, and then the coefficient right here is very, very close to no regression, that means a very simple and original version of linear regression. But if you increase the weight of the lasso, and you can see that right here. If the alpha value, the weight bigger, okay, for example 0.07, you can see that one of the parameter, which is NOx, okay, its coefficient now becomes 0. That is because we ask the optimization function to minimize the sum of the coefficient, right? So if you keep increasing this value, you can see that loss of coefficient become 0. Okay, because the weight is very large. So in this case, we can see that from the perspective of regularization, NOx chaos they might be 0. Okay, but you know, if the weight of the lasso or ridge become larger, okay, it really doesn't make any sense if you do so. So usually we will simply just use a very small value of the weight, the alpha, okay, so that try to make the model to be simpler, not that complex. Okay, so you can take a look at this one. Okay, and again, you can also use ridge regression, but as we mentioned before, when you use ridge regression, there are some mathematic reasons that if you use ridge regression, if you increase this value, okay, the corresponding data table right here, okay, data, the corresponding coefficient will be close to 0, but it will never be 0. Okay, you can see that we can adjust this value, and those coefficient will smaller, but it will never be 0 because there are some mathematic reason. Okay, so if you want to make sure your model is become simpler, to not to overfit the data, you can apply regularization. Okay, and there's even a elastic net, which means you can use the L2 value and L1 value, and you can simply just adjust the weight of L1 and L2. Okay, but sometimes we simply just don't use this one. Okay, use L1 regularization is good enough. Okay, so that is regularization. And as you can see that if we apply some other algorithm, for example, some other algorithms, okay, sometimes you can see that some algorithms, they also apply L2 regularization and L1 regularization. So it is a common sense that you should apply L1 or L2 regularization on your regression model, although it is not the original version, but you should apply it. Okay, so that is overfitting. Okay, and the next thing I would like to show you is let's talk about for example that would be a good one. Okay, that is the hard disease data set. So we have numeric data and we have categorical output. Okay, so as we mentioned, for some algorithms, it is not possible to use categorical data. For example, you cannot use linear regression, you cannot use logistic regression and SVM on those categorical data. But actually, when you use, for example, when you use logistic regression right here, we can still run the program, okay, even if there are some categorical features in it. That is because before Orange feed those data point into logistic regression, they will further transform categorical data into numeric features. So, for example, if the gender right here is either male or female, Orange will generate two new features, and one is called male, the other is called female, and the male will be 1, okay, and female will be 0. We call it one-hot encoding, okay? So it depends on how many different classes in one categorical data feature, okay? If we have two different values in one feature, and it will create two additional features. One is called male, the other is called female. Okay, so we simply just use binary data to represent it is either female or male. Okay, so for example, if we have okay, take a look at this one. Okay, this specific feature, okay, it's either up sloping or flat or down sloping. So for this specific feature, Orange will create 3 different new features. One is called down sloping, one is called flat, the other is called up sloping. So for this specific data, up sloping is 1, and its new flat feature is 0, and its new down sloping feature will be 0. So that will be 1 0 1 0 0, and for the flat it will be 0 1 0, and that will be 0 0 1. So that is called one-hot encoding, so that we can transform categorical data into numeric data. So we can then use algorithms that was designed for numeric data. Okay, and when we talk about clustering, okay, for hierarchical clustering, we mentioned it before. Okay, first we need to calculate distance matrix and connect the distance to hierarchical clustering, and there are some features. We have some features, and we use those features to calculate the distance. And here are some distance matrix functions. Okay, so then we can use hierarchical clustering right here. Okay, and because it is very difficult for us to observe those high dimensional data, so basically I want to introduce this one. Is MDS. Okay, so for MDS, okay, you can plot the high dimensional data into 2 dimensions right here. Okay, so the idea is that the distance in high dimension should be very close to the distance in low dimension space. So of course it has some algorithm to help you to plot this value in low dimension. So if you want to observe data in low dimension, you can use MDS. Okay, and for DBScan, okay, but it is pity that you cannot output the value of DBScan. The only thing you can do is to populate which cluster it will be clustered into. For example, for DBScan in this data sample, okay, it has class 1 and class 2 right here, and you will specify if this value is a core point in DBScan, or it is a non-core point in DBScan, or it is outlier of DBScan. Okay, but you cannot plot the value, you cannot plot it on, you cannot plot if just like we did in Python. Okay, you simply just get the result. Okay, and another thing I'd like to share with you is the for example, okay, if you use some algorithms, okay, for example, logistic regression and SVM, and you can see that if we connect a data table right here, and you can see that for every model, okay, for example SVM, although you can directly get the class, okay, of this data point, okay, so that is the result of SVM, which is class 1, and that is the result of logistic regression class 0, and you can also obtain the corresponding probability, okay, of different classes. So it might be useful because for logistic regression, okay, you can see that there are some classes, okay, there are some data points which belongs to class 1 in logistic regression, and you can see the probability right here, and you can see that for some data point, okay, although its probability of class 1 is 75% and 60%, and some of them even they are very close to 0.5, very close to the boundary line, but it will be also be classed into class number 1, right here. But think about one thing, the probability right here is 50%, right? That is 48%. Basically those data points, okay, they have very close probability, which is close to 50%, but you know this one is classified into 1, and this one is classified into 0. But it would be better for you to consider to use the probability right here, okay, to specify it should be classified into 1 or 0, or data around the boundary line should be, you know, reconsidered. And in that case, maybe you can use the second model, for example, using SVM, okay, to think about maybe some of the data points are just around the boundary line, okay. So you have to think about these things, okay. It is not necessary use 0.5 as the boundary line. You may consider the result of other model, okay. So maybe you can use a weighted sum to see if the average probability of class number 1, for example, this one would be 45%, 54%, and this one 66. So you average it, it will be something like 60%, okay. And this one, although it is 44% by linear regression, logistic regression, and this one is 40% by SVM, so the average is 42, right? So it makes you feel more confident to classify this data point to class 0. Okay. So let's take a look at this one, preprocess. Okay. You can do some preprocessing. Okay. So right here we have several several functions can be used. For example, if your data set has some missing value, you can simply just use the input missing value preprocessor. Okay, you can input the average value, which is the mean. Okay, the mean value we talk about in the missing value section, right? Or use the most frequent, that is the mode value. Okay, we replace it by the random value, or simply just remove. Okay, and you can normalize it. Okay, you can do standardization, you can do normalization. Okay, and you can perform principal component before you analyze those data. Okay, so you can combine all those things before you apply the data with certain algorithms. Okay, so that is preprocessor. Okay, So I think that is okay. The next one is the box plot. Okay, and you can see that it will generate the bar plot. Okay, so for example, age, it is a numeric data. So it says that, okay, we have two different classes. Okay, one is hard disk, right? It's normal. The other is abnormal. For the, I don't know, that is normal and normal. Okay. Oh, 0. Okay, 0 right here. So that is, I think that is normal. Okay, so for the normal, there are points. Okay, the age right here, that is the Q1 and Q3. Okay, that is the average, and that is the standard deviation. That is the mode, and you can see that is bar plugs. Okay, so that is the that is 1, right? That means your diameter narrowing is 1, and the corresponding age is, it has a larger average, larger mode, larger Q1 and Q3. Okay, so you can use this to make an observation on your data. Okay, so I think that is okay. We will talk about even more orange widget later in the class. Okay, so we can stop right here.